And some things about the SecOPERA and the goal of this event. We plan to present to you to summarize the project overview, to talk about the scope and the methodology that we have followed so far. We're going to present the main achievements and specifically the first integrated version that we have with the MVP. We have just passed our first review meeting with this, and we will also present the progress with the pilots. We have the SecOPERA project has 2 pilots. We have presented them again in the first info day for the ones that have followed the 2 events, and we will present you now the updates. I am George Hatzivasilis. I'm from the Technical University of Crete, which coordinates this project. And the rest speakers are the Apostolos Fournaris, who is the technical coordinator. He's from Athena Research Group. And Stavros Fostiropoulos is from ITML and has the role of the integrator of the SecOPERA platform. And then you will see the pilot presentations. From the first pilot from Pino Innovation, we have Chris Kotselidis and Simon Volk from the Voxel company. And from the second pilot, from Green Citizens, we will have 2 co-founders of this company, Alexander Boudon and Francois Hamon. This is the overall agenda. We start with some introduction. Apostolos will present the overview of the technical aspects of the project, the system architecture. Then Stavros will present the MVP version of the current platform. We will have a short break, and then we will have presentations of the 2 pilots. And we will close the meeting with a Q&A session, and we will also share a questionnaire where you can provide your feedback and to us. Here are our means to communicate with us, our website and our social media accounts. I will also share them at the end in the chat. And yes, that's it for me. We can proceed with the next presentation of Apostolos.
Hello everyone, good morning also from me. Let me share my screen so that I can start the presentation. You should be able to see my screen. Okay?
Yes.
Great. So what is SecOPERA about? So let's speak a bit about the motivation behind the project and what we try to achieve in SecOPERA based on what is out there in terms of open source solution and their security. So when it comes to open source, not only open source, there's a lack of a holistic assessment flow that involves all entities of an organization in order to figure out cybersecurity issues that involve an application that a software and or hardware solution that an organization is building. There are a lot of tools out there, proprietary and open source, but there is no easy way to actually integrate them in the unified security assessment flow to audit a software and hardware solution that may include open source components, or it consists exclusively of open source components. So this kind of a holistic assessment and auditing approach also lacks a holistic reporting mechanism. So you get tools that each one of the tools provides their own reporting way, or there are of course some standardized way to report vulnerabilities, but at the end of the day you don't have a collection of different tools provided you all of them in a uniform way a report at a high level of what is happening in terms of security vulnerabilities in your software, right, or hardware. And that goes beyond assessment, and it passes also through the flow of hardening. So how do I provide very focused yet holistically organized ways of hardening software hardware solution, including open source, which that kind of mitigate existing vulnerabilities. And it seems that, and that's true actually, that there is no one for all solution to hardening and assessment. And we need to take into account the specificities of each of the open source solutions that are out there. And this is approached in a very specific way in SecOPERA. So we understand in SecOPERA that not all code base should be assessed and hardened in the same way. And that led us to the overall concept of the project, which is to provide one-stop hub for complex open source software and hardware solutions, so that the users of that hub, the implementers, the designers, and the operators are able to they have the means to analyze, assess, secure, and harden and share open source solution, and not only open source solutions, so a combination of open source and proprietary solutions. To do that, we have a framework that provides support for the DevSecOps lifecycle of any open source system. At the end of the day, we provide a kind of a hardened version of that open source system, or of the open source / proprietary system, which includes, among other things, what we call security guarantees. And with that, we call them in SecOPERA secure flows. So key aspect of this approach is the decomposition of any open source application into different layers. In our case, there are 4 layers that we identify as being important. One of them is the device layer, where we focus mostly on the device on which the software is being developed, or security vulnerabilities that are related to the device on which software or hardware is being used. There's always the application layer, which involves purely application-related assessment and hardening. And there's also the network layer that is related to source code that is focused on network communication, as well as the runtime assessment of a network. And then we also have the cognitive or intelligence layer, if you want to call it, practically deals with the part that exists nowadays in many types of software, which is the existence of an AI model and how to assess the model itself and protect it eventually. So each layer, so practically you get an open source solution, and we decompose it into these 4 layers so that it can be assessed per layer. So we kind of create through SecOPERA tools, modules, primitives that assess an open source solution per layer. So you decompose the open source solution, practically tagging the open source solution software and hardware on these 4 layers, and then you apply specific specialized assessment mechanism and hardening mechanism per layer. So this allows us to kind of fine-grain the assessment of an open source solution, as well as the hardening of it. We also have a debloating mechanism that is part of the hardening of the open source solution. Again, per layer, we debloat the code so that we remove unnecessary parts of the code that could that increase our attack surface. So eventually, vulnerabilities are reduced just by reducing the code base, practically reducing the amount of code that's in an application, which removes part by debloating. We remove parts that are actually not needed. And we also have an updating and patching mechanism that is supposed to keep the the open source solutions secure over the course of time, as they get updated and changed over time by their developers. We also update and patch them within the SecOPERA platform. Quickly, a few examples of components that of open source components that will belong to some layers. So for the cognitive layer, we can identify, for example, open source machine learning or deep learning libraries, or models developed with those libraries, as well as datasets for training and testing, open source datasets. For the network layer, we look into network stacks for various layers of the OSI model or the IP model, focusing a bit on the embedded system domain. But we also focus on network stacks for security, like OpenSSL and OpenSSL libraries. But we provide hardening of those libraries. But we also consider the network as a runtime system, and we introduce into this runtime system penetration testing kind of mechanism, as well as security intrusion detection systems to detect vulnerabilities and possible attacks at runtime. At the application layer, we use open source system libraries, and also any software that performs some functionality that is not fitting in any other layer, that could have some vulnerabilities, with a bit of a focus again on the embedded system domain, or the Internet of Things domain, we call it differently. And we also have the device layer, when we're looking into it, how to harden RISC-V architectures, which is an open source processor architecture, and also on hardware IP cores described in some HDL language that could be leaking sensitive information, and they can be also open source. And we're focusing a bit on side channels. You can see here the concept of the overall architecture in this flow. So the SecOPERA framework, you get an application, you decompose it into these 4 layers, and you pass it through the SecOPERA framework, and you assess the system and harden the system per layer. And you pass it again to the SecOPERA secure repository, where you have the secured version of the application. And along with that, which each one of the secured version application, you have the secure flows, which provide information that are related to what has been assessed, the vulnerabilities that are found, and how they were mitigated, as well as the dependencies between the various components of an application belonging to each one of the layers. The idea is to have a kind of a security guarantee associating the secured version of an open source solution that can be viewed by a third party, and can provide some trust on that the solution that is out there is considered secured. That doesn't have any vulnerabilities, or have small vulnerabilities. SecOPERA consists of 5 pillars, in line with what I said already before. So we have the decompose pillar, the audit and assessment pillar, the secure and adaptation pillar, as well as the update and patching pillar. As expected, in the decompose part, you get the open source solution, you analyze it, and you generate a dependency graph, and from that you assign the parts of the code to specific layers. That's the decomposition process. And then we have the audit and assessment pillar, where you have various different types of assessments taking place, assessments per layer, security assessment, security testing. Actually, we have 2 types of assessment. The one we have what we call static assessment, which is practically a variation of a threat intelligence and risk assessment mechanism, looking into known vulnerabilities that are out there for assets of the existing in the open source solution and assigning known vulnerabilities to those assets. That's the static part. And you have a dynamic assessment, which is practically security testing. This is happening per layer with assessment tools that are focused on each one of the layers. And also, this includes any penetration testing vulnerability assessment. This is especially focused on the network layer, for example. And eventually, you get a report for all those tools and forward it to the SecOPERA platform and the hub as a whole. In the secure pillar, we develop modules that can mitigate vulnerabilities that are found in the audit and assessment pillar. And those modules, again, are developed per layer, so they can kind of they can have a fine-grained approach on how to mitigate vulnerabilities. The mitigation itself is in the adaptation or the adapt pillar, where you actually integrate these secure modules um, in the right places within your code. That is, of course, decomposed to layers. And you also perform the code debloating. And the final pillar is, of course, the update and patching pillar, where you monitor the open source software and hardware repositories for updates, but you also monitor for the assets that exist in the open source solutions for new vulnerabilities. And we kind of provide updates and we patch the system, the open source solution, practically kind of rerunning the flow of SecOPERA when you have an update. Practically a clever rerun of the flow, not the whole flow itself. So this is the conceptual architecture. It kind of describes what I just said. The only, let's say, I can focus here to just say that we kind of split the concept itself to an architecture that consists of a few engines. So we have the decomposition and dependability engine, which takes the code from some repos, or even not even a repo, you just upload it as a developer, your code in a tar file, and then we do the dependency discovery, and eventually you do the decomposition in the 4 layers. Then we have the security audit and testing engine, which is performing practically the assessment per layer for device layer, for network layer, for application layer, for cognitive layer, as well as the known vulnerabilities assessment itself. Then we do code debloating and reassess the system with the debloated code. And eventually the found vulnerabilities will be mitigated using the secure module pool, which includes secure modules for hardware and software, again, structured per layer. And the security assessment process takes place, and eventually all information is collected and reported in the secure flows, practically the secure guarantees, that then are stored in a repo along with the secured code, and stays there and to be constantly monitored for updating, for checking the updates existing either in the original repos of the code or in new vulnerabilities that are found, and then the update and patching mechanism that kind of follows. The actual reference architecture is a bit more well defined than the previous one, and that's our starting point in developing our solution, as you will see later on. So again, you have the engines, and you have a kind of a cloud system that practically includes the backend and the front end of the whole hub solution, as well as the data pools where all the data are being stored. Practically, we identified 2 flows, two processes, if you want to call them differently. The security assurance flow, which includes the decomposition, the assessment, the hardening of the component, and generation of security guarantees of an open source solution. And we also have the update and patching process, which kind of starts from an update, from detecting an update in the original open source solution or new vulnerabilities that have been discovered, that and triggers a kind of clever security assurance process, which updates with performance assessment again and hardening just for the updates that have been done in the open source solution itself. So yeah, a few where we are now in each one of the pillars. For the compose pillar, which of course related to the composition engine, we have collected open source code and also executables from the pilots that we have in the project. We have decomposed them already into the SecOPERA layers. And this is at the moment, it was a manual process, but now we're moving to a semi-automated decomposition process that can auto-discover, for example, assets of the open source solution and blocks of code that belong to specific layers. The outcome of this decomposition will be a JSON report that is fed into the SecOPERA platform for further analysis. For the asset and for the audit and assessment pillar, we have the main operations are related to security audit and testing engine. And we have created assessment modules, the architecture, the design, and the implementation. We have done already some experiments with the pilots, using their open source code that they provided to us, as well as some proprietary executables. Continuing the flow from the decomposition of that code. And we expect to have a full prototype of all assessment primitives by the beginning of the next year. That will be used internally for further integration of those modules in the platform. And also we've done work on the knowledge-based vulnerability assessment, this component here, which is offered as a service. And we already have a first integrated version of that in the platform. You can see here a few of the modules, the assessment modules that we've created were created by the partners of SecOPERA per layer. For the device layer, we have an assessment module for side channel attacks. For the network layer, we have penetration testing toolkit, as well as dynamic vulnerability assessment toolkit, as well as an assessment discovery and profiling module. For the application layer, we have a few primitives that can support the assessment of any application, including a call graph generator for Python, a call graph generator for C code, a static C source code analyzer based on Framacy, the well-known Framacy tool. For dynamic testing, we have an AI-assisted fuzzing tool on which we can also include mutation prioritization strategies that are kind of speed up the fuzzing process itself. For the cognitive layer, we have a series of toolboxes that can assess for various different types of machine learning related attacks, including privacy related attacks or adversarial attacks, like for example, evasion attacks, membership inference attacks, model inversion attacks, and model extraction for extracting the model structure. For the secure pillar, which is practically generating the primitive module for hardening. For each one of the layers, we have several different primitives that have been developed, and will populate the secure module pool itself for providing the necessary component to do the hardening itself. So for the device layer, we're focusing a bit on the side channel attack resistant, as well as to provide the next generation quantum resistant generation of crypto primitives for public key cryptography. And we have a series of IP cores for post-quantum crypto related components. And we also have a RISC-V softcore distribution that includes protection against code reuse, practically by having a very elaborate CFI mechanism into the RISC-V structure. For the network layer, we have a trust-based intrusion detection prevention solution that can be deployed on a running system. Then a quantum-resistant network stack, which includes TLS 1.3, post-quantum TLS 1.3 for embedded system and for general system, but also specifically for embedded system, we also implemented the ad hoc protocol in post-quantum in the post-quantum domain, practically doing again for embedded system and low resource systems, secure communication on the application layer using this ad hoc protocol. We also have um, a trust execution environment, setting up with practically by having dynamically configurable IP cores on an FPGA that can support the trust execution environment. For the application layer, we have the software part of the shadow stack and landing pad enabled RISC-V support. And we have already started developing our code debloating primitives to be used in the adaptation pillar for code debloating later on. And for the cognitive layer, we have several toolbox that kind of support, provide guidelines on how to mitigate membership preference, model inversion, and machine learning evasion types of attacks. And also we have the FastML-H solution, which practically do machine unlearning when some class is kind of mistreated in a model during inference. For the adaptation period, that's where the actual adaptation takes place. This is a kind of thing that we currently work right now, and the adaptation engine itself. So the idea is to have the secure module developed on the secure pillar. We have already first versions of all those modules, and then to kind of create a deploying mechanism and also kind of use those modules into the security hardening process of the project. And the update and patching pillar is something that has just started in its development. And it's actually a process that includes the secure assessment and a few additional things. Practically, we're working on the monitoring of the update of the updates taking place so that we can trigger the updating patching process itself. As I kind of hinted already, we have two main processes or two main pipelines that we work on. We have identified three types of users: the designer, which has a high view of the whole thing; the developer, which is the development of some code, and he wants to get the assessment results in order to harden the code itself; and the tester that's performing the security assessment. So the designer is kind of the manager of the whole thing. The developer, the tester kind of work collaboratively using the SecOPERA platform to eventually provide an outcome based on certain KPIs provided by the designer that would be considered secure. And all of this, of course, process provide detailed, holistic reports to the designer and also to the other types of users that fit the type of user itself. So the designer will have a high-level report, while the developer a more low-level report coming out from the existing tools that are supported by SecOPERA. As I said, two processes: the update and the security assurance process and the update and patching process, which kind of is an extension of the security assurance process. Just to highlight a bit the innovations that we have in the project. So first of all, one of the innovations that are related to discovering threats, this layered type of approach has triggered a kind of different threat intelligence or threat modeling approach also. So we based on the STRIDE model, we kind of extended the model to be able to support this various layers of that we support in SecOPERA. So instead of having this STRIDE based vector for threats, we now have dimensional matrix where we also have columns for each type of each layer of the of hardware or software. For the security assessment primitives, we have several innovations related to all the layers practically. For example, the side channel assessment module is supporting assessment using machine learning and deep learning side channel attacks, with several innovations on the PQC domain, post-quantum cryptography domain. We're doing trace collection in a very fast pace with high flexibility and very easy to start the trace collection process for the side channel trace collection process. We also have a dynamic vulnerability assessment that's kind of automated for the network layer. Several innovation extensions in the form of plugins have been introduced into Framacy that is behind the static C source code analyzer for the application layer. We have a new fuzzer for mutation prioritization strategies and also AI-based fuzzing, which again themselves are providing several innovations on their own. And we also have an assessment toolbox where we have a coherent and innovative privacy and adversarial attack assessment toolbox, protecting against various different types of attacks, and including the FastMLH, which is a mechanism that allows us to provide a quick result if we need to remove one class, for example, in a model, without being focusing on speed rather than on full coverage. Similarly, for the hardening primitives, several innovations there. We have, of course, the new RISC-V distribution, which has been approved by the RISC-V association. It kind of has CFI as in the instruction set of the processor, so an extension of the instructions to support this. And it's kind of well documented, and it's kind of mainstream nowadays. We have this quantum resistant security protocol implementation of TLS 1.3 in EDCOC. For EDCOC is the first known implementation of EDCOC that is quantum resistant as far as we know. Kind of submitted in a conference that this work on EDCOC. The trust-based intrusion detection prevention solution, which includes next generation IDS mechanism, and this fine-grained project dependency graph, so FPDG, which is it provides deep call graphs even from different Python files that can be used for code debloating very efficiently. The SecOPERA itself as a platform is kind of innovative because it's a kind of KPI-driven solution that provides assessment and hardening in an automated way, or a kind of helping the types of user to do the assessment and hardening. It incorporates very many different assessment and hardening tools and services in a unified whole, and provide also holistic reporting based on what we had initially as a motivation. So we have two pilots. They will be analyzed further later on. So we have the secure supply chain in the automotive industry pilot, which includes two partners, pilot partners Pinot and Vauxhall. This has two use cases. The first use case called Velopera, it involves open source solution. They're practically related to the board, the embedded system board that is on the bike, and the intercommunication of that board with the cloud system. It involves several components, including hardware, firmware, and software. And there's also the SecOPERA use case, which is similar to the use case one, but has both open source parts and proprietary software parts, which allows us to kind of provide a more holistic and realistic also assessment and hardening which you can find in the industry, including some parts that open source and some parts that the organization or the user of SecOPERA wants to keep private. And also involves different types of users, even different categories of users, even of the same type. And two pilots, the second pilots is the water management IoT critical infrastructure by Green Citizen, which includes devices, IoT devices deployed for water management, which is communicating through BLE, and also a cloud service with a web application on the mobile phone, but also a cloud service itself, connect actually the web application to the cloud service that provides a series of services of monitoring the water management itself. So we have three use cases. One of them, first one is related to the IoT device. Its communication. The second one is related to the platform, the cloud platform. And the third use case is related to the cognitive layer, the AI models that the anomaly detection practice, AI models used by the platform to provide, to show to the user various anomalies. You can see an example of how the SecOPERA can be architecture is adapted for the pilot. So this is for pilot one. We monitor what the pilot wants and who kind of highlighted which are the important components that the pilot needs, which are the non so important components, the critical and not critical one. And we've done that for both pilots, of course, and the use cases. And we also have adapted these two processes. This is just for the assessment process of the project into different types of users and provided also a lot of more details on how these blocks here should be done for the various use cases. This is for use case one and use case two, pilot one. And you can see that for use case two, we have proprietary code. We have developer types of users, but from both of the two partners, and with different access to the code itself. And we need to provide we evaluate the platform based on that scenario. And similarly for pilot two on the platform itself. So yeah, to wrap it up, so this is the SecOPERA architecture where we are now. We have our first implementation or development-based architecture based on the reference architecture, where you can see a bit more analytic what happens behind the scenes. And you will see the realization of that deployment application in the MVP version of the solution demonstrated later on by Stavros. And that's it from my side. I hope I didn't take too much time. Any comments?
Hello, I think we are good. We can proceed with the next presentation with Stavros that will present the demo of the current version of the platform. Hello, Stavros.
Yeah, hello everyone. Good morning. Thanks, Apostole. Okay, let me share my screen. I guess you can see my screen and hear me well, right?
Yes, we see the login page of the SecOPERA.
Okay, great. Okay, so a short introduction before we jump into the SecOPERA platform. So the plan for this slot is first to show a live demonstration of the SecOPERA framework, currently the MVP version, and then depending on time to show a video demonstration of the technologies, the primitive technologies that have been already integrated in this SecOPERA platform. So the idea is to focus more on the functionality of the integrated framework itself, discuss more about the collaboration between different users, rather than get into much detail on the technologies, since this information will be provided in the videos right after the live demonstration. So, as Apostolos mentioned, we have identified three different types of users: the designer, the developer, and the tester. In terms of their involvement, we will present a full cycle of assessment and handling using the SecOPERA framework. This is separated in different iterations in two distinct phases, actually. In the first phase that users are involved, this is the actual assessment of SecOPERA open source solution. Starts by the designer who's creating the project, and then passes the token to the developer and then the tester. And then the second phase is about the evaluation of the findings, where it's the vice versa. The tester communicates with it's a bottom-up approach. The tester is communicating with its collaborators, communicating with the developer, and then the developer with the designer. Start with the designer. Once the designer is logging into the platform, this is actually the main landing page for all three type of users. The designer is presented with a screen with already existing projects. As you can see here, we have already created two different projects related to our pilots. So the options for the designer is to enter in an already existing project, or creating a new project from scratch. Let's see how it works. So by selecting this option, the designer is creating a new project. Here are the fields for setting a new project. Let's say that project X. Enter the project description, like description, and then the designer can select from a drop-down list the developers that need to be appointed and work in the project, and the testers. Finally, the designer is responsible for selecting the KPIs under which the findings of SecOPERA will be evaluated. The KPIs are also selected from a drop-down list, and they are linked with the technologies of, they are directly linked with the SecOPERA technologies. We can add an extra KPI here. And creating a new project, you can see that this new project text has been appears in the landing screen. Now, by selecting View button, this is actually in this screen. The designer can see an overall description of the project ID, the description, the project status, which is in progress, and the names of the assigned developers and testers. By selecting this Show Select KPIs button, the designer advances in this KPI info panel, where the designer can see the selected KPIs, and right next there is a field for the designer to put a comment. This comment will be helpful for the developer and the tester, and will provide them with guidelines on what kind of assessments need to be done. Okay, let's see comment here. By clicking save, this info panel is saved, and next action actually is going to this view report button. Again, the KPI selected are presented in the upper screen. There are different columns. In each column, there are columns with the comments by the designer, developer, and tester. Since the project was just created, we don't have any comments by the developer and the tester, only this comment by the designer. And you can see here that in this column that we have a box which indicates if the KPI has been fulfilled or not. On the lower screen, the designer has available, let's say, an aggregate report of the SecOPERA project. For the time being, you see that this is blank since the project has not been assessed. But when we return back to after the assessment, you will see that this report is going to have findings inside. That was all regarding design and user. Once all these are completed, the designer requests an assessment. So he sends a request to the developer, so the assessment of this specific project to be initiated. So the developer has been notified to log in the platform and start working in the project that has been assigned to. So now we log in with the developer account. Again, the developer, the landing screen of the developer is identically the same as that of the designer. He is presented with the available projects. He has been notified to work on this project X. However, at this point, let me tell you that we plan to showcase all the functionalities and all the pipelines in this project, the Raymond Combat Ray project, which is related to Pilot 1. The reason for that is that, as Apostolos mentioned before, we have the decomposition, the output of the decomposition engine is provided offline, which means that we have already provided decomposition output for this project. And for the time being, since it is under development, cannot be provided automatically when you use the platform. So let's enter this screen. This is the main landing screen of the designer. Again, in the upper screen, we can see the description of the project, ID again, description, status, and assigned developers and testers. While in the lower part, the developer can see the list of components, the decomposition output, actually, which is a list of components that comprise the open source solution. Those components are broken down in 4 different layers, also mentioned by Apostolos. Those layers have been identified within SecOPERA, namely the device layer, the application layer, the network layer, and the cognitive layer. We have also a list of components of closed source components. However, you see that for this specific project, no closed source components have been identified. So the developer is responsible for performing a list of action by clicking on each component. We see here that there are several list of actions starting from editing a component. So here the developer, for example, can change the CPE or change something in the table of the component. Next, the developer can upload a file. So he can upload additional code or additional information relevant to this specific component. Can download the component itself. This is useful for offline assessment with the available tools, with the available offline tools supported by SecOPERA. View assets. I will provide more information on it, and actually view an aggregate report of the results of each tool and service on this specific component. Now, by clicking View Assets, what is happening actually is initiating a knowledge-based vulnerability assessment for instance, for the selected specific component. Doing that, the static threat profile for this component, which is also cyber asset, is built. So by clicking that, SecOPERA system integrates with open repositories and start receiving vulnerabilities, weaknesses, and threats. So by clicking in this specific cyber asset on this action button, we see here that the vulnerabilities received the vulnerabilities related to this cyber asset that are presented in this part of the screen. Those vulnerabilities are received by the Organised repository. For each vulnerability, by clicking on this action button, a list of weaknesses are received. Here we have only one weakness. Those are received by the OpenMeter repository, while for each weakness, a list of threats appears by the respective repository. Besides building the static profile, the developer can also further extend the findings of the decomposition engine by he's being able to upload a new CPE that has not been identified during the decomposition process. Or can upload a new SBOM file. It can do that by either clicking on this button or simply by going back to the selecting components by editing the component, changing the CPE, adding a new CPE, and so on. Okay, so that are the main responsibilities of the developer. Having finished with those responsibilities, the developer can also provide a comment here as a guideline for the tester. So the tester has a, let's say, has a roadmap on what kind of components can assess and what tools needs to be used in order to assess those components. So let's put a comment in these fields. For instance, you can request an assessment on the component, let's say number 20, saves this KPI info panel. And last action is to request from the tester to start the assessments. Sending a request. And yeah, let's, and now it's turn of the tester to log in. Again, same landing screen. The tester has been notified to start assessments on this project, Raymond Compact Ray. So enters the main screen. Again, a high-level description of the project. Similarly to the developer screen, the tester is presented with all the information of the decomposed open source project. The open source components, open source and closed source components per layer are visualized. However, what differs is the rights of the tester. So if you click on a random component here, you can see that the tester is not allowed to change, to modify a component or editing, uploading a new file, providing additional information to a component. So he's allowed to download the file for offline assessment, view the list of vulnerabilities, weaknesses, and threats, and view again the aggregate report on a select component. So the pipeline continues with selecting the KPI panel. As you can see here, the tester can visualize the comment of the developer. Indicatively here, you can see that he needs to do an assessment on component 20. So now, navigating to this specific component, we see that if we click the view report button, we see that there are no results here, since it makes sense, since no assessments have been taking place so far. And now, actually, the main responsibilities of the tester is to run the assessment using tools. He can advance to this tool screen here. We see here all the available tools and services, again clustered in the SecOPERA layers. For the in the current version, the network, the penetration testing toolkit is integrated as a service in the SecOPERA platform from the network layer services. From the application layer tools, we have integrated the CCC call graph generator for embedded system and the static source C-source code analyzer. Those are integrated as tools, and they can download offline for further assessment. And among the cognitive layer tools, we have integrated the membership inference toolkit. So let's do now. Let's see how the only service integrated for the time being is the penetration testing toolkit. Let's see how it integrates in the SecOPERA framework, in the SecOPERA system, and how the results are automatically being updated in the SecOPERA database. So by clicking use here, we see this is the main landing screen of penetration testing toolkit. We select the project ID, click view data. I will not go into much details on that since we have a video demonstration right after the SecOPERA live demo. Let's do an assessment of component 20 as the developer requested. So the assessment has been finalized. Let's go back to the SecOPERA screen. As mentioned, this was the list of tools, and now we will see the available results from the penetration testing toolkit in this same component number 20. Again, selecting this component and click the tester clicks view report. We see now that the results from the penetration testing toolkit have been integrated in the SecOPERA system. Similarly, we have there are also results on other components from offline assessments. For instance, in this component number 7, if we click on the view report button, we see an aggregate report with results for the specific components. We have available results from the static C-source code analyzer and the C-call graph generator for embedded systems. The resolution is not good. It's not that good in here, but we have also a separate demo video for that as well. Having finalized with the assessments, the tester needs to evaluate the results and provide comments for the developer to start the second phase of the assessment hardening life cycle, which is the evaluation of the findings. So the tester can provide comments here for the developer, like let's say like that the component 20 has been assessed. Those are indicated comments, okay? And then needs to request to send this report back to the developer by clicking this send report, and then the developer logs back in the platform. Select the project under assessment. So select KPIs, and we see here that the comments of the tester have been integrated in the KPIs of the panel. Now the options of the designer are to either provide additional information in the select component by clicking the edit component button, or using hardening and hardening tools from these from this pool of secure modules. By clicking this button, the developer advances in this new screen. Again, we have primitive secure and hardening tools that are categorized in different in the identified SecOPERA layers. For the time being, we have not integrated any secure hardening tool. We plan to do that in the following SecOPERA system release. Having performed hardening on the components under assessment, the developer opens the KPI panel, and now it's time to provide comment for the designer. So guide the designer and help him understand if the specific project, if the specific KPI has been achieved or not. So he can provide a new comment like something here, and requests and notifies. Now the developer notifies the designer. We see that the developer is the intermediate user. He can either request reports from the tester or notify the designer that an assessment hardening lifecycle has been completed. So again, the designer needs to log in back to the system. Now the designer has all the picture of the assessments that have been performed in this specific project. He can see the comments from the developer and the tester. By clicking on this action button, you can see an aggregated report with the components that have been assessed for this specific project per layer. The tools that have been used for the assessment of those components here. And finally, to go through the KPIs that was set in the beginning of in the creation of the project, and to decide based on the comments of the developer and the tester if the KPIs have been fulfilled or not. In case they have been fulfilled, he can click on this fulfillment button here, and let's assume that all the KPIs have been fulfilled, and he can go back to the main screen and select complete in case that all the KPIs have been fulfilled. If a KPI has not been fulfilled, then he can request a new iteration of assessments from the developer and the tester, and reevaluate the findings after that. I think this was more or less the pipeline of actions and how the different type of users collaborate in order to perform a full assessment of an open source project, of an open source solution. I don't know how much time we have. We have actually time for some video demonstrations. Okay, let me. So now we'll see a video demonstration of the penetration testing toolkit, the one that is integrated as a service in the current platform. Can you see the view screen?
Yes, we can see the screen.
Okay. Do you listen to the narration?
We see the screen, but we do not hear sound.
Okay. So Yeah, I'm not sure how I can do that.
I think it is an option where when you share your screen.
Okay.
You have also to share the sound.
So yeah, I think it's in the more under in the toolbar. So with the dots on the right.
Again, no sound. I think you have to stop sharing and share again and check the correct configuration.
The penetration testing toolkit
Okay,
is
now we hear it.
a SecOPERA for network assessment. The overall solution is provided as a service and is accessible by the user via the SecOPERA dashboard. The pentester selects the network component that will be analyzed for a new project. Then, network mapping is performed for a given IP address and a range of ports. The main assessment can now begin. A series of tests are performed to examine if the component is vulnerable or lacks protection mechanisms against rigorous port scanning, denial of service attacks, login cracking, or security downgrade due to support of weak or deprecated ciphers. In the demonstrated example, the first two tests were successful, while the last two ones failed. Therefore, two vulnerabilities are reported for port scanning and DOS attacks respectively, following the format of Common Vulnerabilities Enumeration of MITRE and the risk evaluation of the Common Vulnerabilities Scoring System of FIRST. The related weaknesses and threats are also reported, based on MITRE's Common Weakness Enumeration and Common Attack Pattern Enumeration and Classification repositories, respectively. The user can collect further cyber threat intelligence concerning known CVEs, CWEs, and CAPEX by providing a valid common platform enumeration identification for the MAP services. Additionally, based on the identified CVEs, actual exploits can be found in relevant repositories like the Metasploit framework that the pentester can further try to launch. Finally, the overall assessment information is summarized in the top of the screen, and the user can examine the overall risk of this component based on the maximum vulnerability impacts, correlate this with the project's KPIs in the SecOPERA platform, and decide the next steps.
Hello, Stavros, you are muted.
Yeah. So based on the agenda, I think we have time for one more video, right?
Yes.
Okay. So okay, this is a video of the demonstration of the pharmacy tool. This is a downloadable tool. Wait.
So The objective of this short demo is to show how the pharmacy C-code analysis tool can be used within the SecOPERA framework. For that, we start from the decomposition output, so the JSON file of pilot 1, and we go in the application layer and select the expressive development framework of ID7. Then we can go to the archive of the source files that come with this decomposition. And first, in order to ensure that we analyze a realistic code base, we start by configuring a target application coming from the example of expressive. Here we will focus on the bootloader, so we take an example from tweaking the bootloader, and we use the build standard build tool of expressive to ensure we have something appropriate. Then the main thing that we need to extract are the command for the build, and particular for the pre-processing that we will need to feed pharmacy with. For that, since expressive uses CMake, we simply have to ask CMake to export this compilation command in the form of a JSON file that we can then copy to the main sources, and there we will start configuring pharmacy. So the first thing that we do is to retrieve information about the compilation toolchain and the target hardware architecture by launching a script that will ask the necessary information to the compiler from expressive. And once we have this information in the form of a YAML file, we can use the standard makefile template from pharmacy to configure the tool. Basically, we mostly give the C source file we're interested in, and a few standard flags for the analyzer, namely the main entry point, which for the bootloader is not main, and a few flags for the EVA plugin, which performs the analysis itself. So the full analysis has been played before because it takes a few time, but we can see its results in the EVET graphical user interface of pharmacy. So the main point is that we have a few alarms here and there, and we can inspect them in the user interface to decide whether this is a real problem that needs to be fixed, or something that is due to the abstractions that have been made by EVA. And here, because we deal with very low-level code and stuff that is completely dependent on the physical architecture, there are a few alarms that we cannot avoid, but which are not real problems. The only points that we have identified here are more portability issues Namely, there are some shifts that are done on signed integers and might overflow, which can be an issue if we are adhere strictly to the C standard, and for which a simple fix is to add a conversion to unsigned version of the type, in which the shift is completely well defined. Once we are finished with the analysis, we can simply generate its result under the Sarif JSON format, as discussed in SecOPERA, and if we have a SecOPERA backend readily available, it would be possible to use the REST API to put this JSON document in the SecOPERA backend. And this concludes this demo, so thanks for watching.
Okay, so that was Pharmacy, an application layer tool provided in SecOPERA. So it's okay. Maybe we'll have time for one more video actually before the break. Let me again share my screen.
Hello everyone, in this video we will discuss the post-quantum crypto primitive hardware IP designed by Industrial Systems Institute for work package 4 of SecOPERA's project. The device layer solution proposed in this work package 4 provides security assessment and security hardening modules related to different devices. Our crypto primitive hardware IP core library contributes to this layer relative to post-quantum security. One of the modules that is inside our IP is the Lithium's digital signature hardware accelerated IP. It was designed in a parametric way for all different modes of operation and for security of the lithium. Also, the security of this platform, the system architecture, is made parametric so it can reused for different IP modules inside of this core library. So a few words of our algorithms of NTT, which is a basic part of the lithium's signature scheme, can be seen here. This is the algorithm of the lithium library. There is a traverse between different number of stages, between different number of inputs and stages, and for each of them there is a processing element taking place. We transform these algorithms to the algorithm on the right, traversing all different number of stages, and for each stage we have a butterfly loop which is based on loops, parallel loops of the parameter B, the index calculation loop, the memory read loop on these index calculations, the operation loop which is based on the memory that was previously accessed in this loop, and the loop that writes back the calculations to the memory. Each of these loops we can see it's based on the parameter B, which is the number of parallel processing element executions. In our case, B equals to 2, but it can be other higher values too. Same logic applies on the inverse entity, exactly the same logic. So we have two modules, the entity, the inverse entity, and then we have the pointwise multiply and accumulate. This is the basic three building blocks of the algorithm. So for each, the input is, the two inputs is the input in and the input mat. As we can see, their dimensions. For each of L times n input, we have L times of entity to transform this input to the entity domain. And then for each L times n, we have the pointwise multiply and accumulate. As we can see, the second input is k times L times n, so we have k times this operation of multiply and accumulate inverse entity and then buffering the outputs. So the final module of the entity and the matrix multiplication can be seen here, the resource utilization. This is the system architecture of our design based on the Vivado system architecture. The IP was designed on VT's HLS code and can be seen here. So this is the processor. The processor communicates with the DMA, and the DMA communicates with a module between two FIFOs, input FIFO and output FIFO to the module. So the module here could be easily removed and insert another IP module. And this is the kind of reusability I was talking about in the system architecture. This is the results for different ARM CPU frequencies. You can see that higher the security of the scheme is, 5, we can see the results are getting, the gain of the IP is getting higher. So in our future work, we would like to take the entity algorithm, which is basically the same in the Kuiper's key encapsulation mechanism, which is a post-quantum algorithm, KEM post-quantum algorithm, and then have a suite for different KEM and DS algorithms that can be used for the post-quantum in an IP library. Thank you very much for your time.
Okay, I think that was all from my side. Thank you.